let me introduce Zeke, who is, when he was 1.5 years old, hopefully this isn't cutting too far into your bio, his early desire in electronics was clearly apparent when he built a light bulb switch configuration, and then he developed an interest by the age of 8 to communicate with the ISS. So I think I'm dangerously getting close to what Zeke wants to say. So at this point, I'm going to hand it over to our very special first lead-off speaker, or keynote, I'd say, Mr. Zeke Wheeler, who has the distinction of being the youngest presenter here at CadenceLIVE.
Can you hear me now? Yes. Hello, everyone.
Hello.
I'm Zeke, KJ7NLL. And before we begin, I'd like to thank Cadence for this wonderful opportunity to present at CadenceLIVE. I'd also like to say that it would be great if you could all hold your questions and comments to the end. Now, let's get back to the presentation. So when I was 8 years old, I wanted to contact the ISS. So I asked my dad, how can I contact the ISS? And he said, well, I don't know. So we got online and we found this place called Eris, and they managed to get a ham radio up onto the ISS. And this was really cool because it meant that if I got my ham radio license, I could talk to the astronauts on the ISS. So ham radio band plans sat on the table for a while, just waiting to be picked up again. And then later, my grandpa found a ham radio class, and this was a weekend class, so at the end of the class there was a test. And in the test, my dad and grandpa passed, but I didn't pass. So then I studied even harder, and then I took the test again and didn't pass again. And then, so a month later, I studied even harder than before and took the test a third and final time and passed with a higher score than my dad. So after I got my license, my grandma Bobby was so excited that I got my license that she got me this ham radio as a gift. So later we learned about a kids net. Now a net is just like this. It's a conference, except it's on the radio, and instead of a place and time, it's a frequency and a time. Now this is a net on a repeater, which means you're broadcasting your signal to something, like this speaker, which is then broadcasting your signal and making it way louder so everyone can hear. Now we were getting something that I like to call scattered signal. Actually, everyone calls it that. But that's when the signal that you're transmitting gets there first and goes straight, but another one of your signals goes off to the side and then goes there, which sounds a little bit like a chirp on the radio. So the answer to solving this is to make a directional antenna, which takes that beam, which goes all the way around normally, and then squeezes it down into one direction, which one gives you more gain so you can transmit with less power and have the same amount of ability to talk to people. And you also can not have that scattered signal with the other one that goes out. You just all file down the beam. So we built this Moxon antenna because it was suggested. And now with the directional antenna, you need to point it somehow. And the reason for this is it's a directional antenna instead of all around, and you have to point the beam to the specific people you want to talk to. So I have lots of Legos. You may have seen this in the demo earlier, and this is just the rotor that we were using to point that beam. Now later we learned about a low signal net. Now a low signal net is the same thing as a normal net, except there's no repeater to broadcast your signal, so you all need directional antennas so that you can have enough gain to talk to the specific people you want to talk to. So we were getting weird polarization. Now, if you're not familiar with polarization, polarization is like a frisbee. If you throw a frisbee like this, but you try to catch it like this, it's going to bounce off your hands. But if you try to catch it like this, you're going to catch it and be able to talk to the other person. So the answer to this is to build a circularly polarized antenna. We chose a helical antenna, and the way this works is it's directional, number one. Number two, it's circularly polarized because it's just a coil wrapped around a core, and a coil of wire where the circumference is equal to the diameter, to the wavelength of the frequency that you're transmitting. So a circularly polarized antenna is also good for space communications because you don't know what orientation the satellite's going to be in, and that makes a big difference when you're trying to match up polarizations with the satellite. Now, this is the finished helical antenna. You can see we have 17 dB of gain there. And now, this antenna is 10 feet long, which gives us quite a bit of gain, and which means its beam is just really filed down to be really specific about where you want to point. And we have a 2-meter reflector because this antenna goes in both directions. It transmits in both directions, which means it has a beam forward and backwards. So we reflect the backward beam all forward so that we're actually doubling the amount of gain forward. Now, we were using, the ISS uses 2 bands, and the reason for this is if you've ever heard a duet and 2 people are singing, one singing a low pitch and one singing a high pitch, they're singing completely different words, but you can hear them and understand them perfectly. And this means, this is why these ISS uses 2 different bands, because you can understand both of them, which is why it's so good for transmitting on one and receiving on the other. But this antenna only has 1 winding there, so what are we going to do about the other UHF winding? I have a YouTube video on that if you're interested in learning more. Now, so we had the idea that since the circumference is equal to the wavelength, we could just make a smaller winding inside of it, which would, because the 70 centimeter is much smaller than 2 meter, so we'd just be able to fit it inside. But we wanted to know if it would interfere with the outer 2 meter winding. And so we simulated it in Cadence Clarity 3D, and we see here that these are just the single windings with just the 70 centimeter or just the 2 meter, and then these are the dual winding propagations with both 70 centimeter and 2 meter and how they radiate their gain patterns. So you can see here, these are really close in dB, which means the inner winding is probably not affecting the outer winding very much. Now this is the same thing as on the last page, except in 3D, and it's just got both windings instead of also the single windings. And you can see the one on the left looks kind of like a rocket. Now, we tried to use our Lego rotor on our antenna, but it just didn't work. We twisted up a Lego pin, never to be used again on a Lego. So what we did is we took this giant rotor. It's an old AC rotor from approximately 1970, and when we got them, they were frozen. So what we did is we replaced the old AC motor and took it out and put in new Lego DC motors. And this is the theta rotor, which moves the antenna in the left-right direction, and you also need an up-down direction to talk to space. So, or you can also call this the azimuth rotor. And that's why big antennas need bigger rotors. So this is the feed rotor, or elevation rotor, and it points the antenna up and down. And you can see we have a potentiometer right there. And what it does is it rotates when the antenna rotates, which means that if we send a voltage to the potentiometer and we figure out what the voltage is when we move the antenna to here, and then we move the antenna to here and find out what the voltage is when the antenna is over here, we can estimate that between here and here, the point right here will be about, we can estimate how much voltage is in 1 degree, which is how we are able to move to very accurate positions with our antenna. Now this is the same thing, except not in this not the feed rotor. This is the theta rotor, and it just moves left and right. So with these new rotors, you need to control them somehow. So we designed this board in Microwave Office, and we etched it ourselves and called it the rocket board because it kind of looks like a rocket. Everything seems to look like a rocket. I have a video on this as well, and that's that. So we calibrated our rotor like earlier, and so now we are using a PWM signal from this Mighty Gecko EFR32 controller from iLabs, and it talks to our rocket board with components on it, which tells our motors where to go. Now it uses a PWM, or pulse width modulation signal, to speed up or slow down the motors by turning them on and off really, really fast, just like a dimmer on a light switch. Now, we are also using Neocleus's TLE library. And a TLE library allows us to figure out the position of the satellite so that we can use our code to actually track the satellite based on the position of the satellite. Now, the TLE uses our time, and it also uses our ground location to figure out where the antenna is based on what time it is, and a bunch of different letters and numbers in 2 lines. My code for this is also on GitHub if you want to try this for yourselves. Now this is a Diplexer board, and what it does is it takes 2 signals, one here and one here, and it takes 2 signals and splits them down into 1 wire so that later at the antenna they can be split out into 2. Now the reason for this is we don't want to have to run 2 wires because these boards are actually really far away from each other. So having diplexers like this may lose a little bit of loss, but it requires a lot less wire. We designed both these boards in Microwave Office. They're actually the same board. And we figured these actually connect to both windings on the antenna. That's why there's 2 of them, one for each band. And we optimized it with point ports, which just go on every single little pad here so that we can place any kind of component that we want in any spot on the board. And this allows us to do up to a 5-element band pass on this board, and that makes it work. Now, we also have a bias key here so that we can send DC through it as well. So we don't even have to run DC wire to power an LNA, or low noise amplifier, on our next slide, and I have a video on this too. Now this is the LNA, or low noise amplifier, and what it does is it takes the really quiet signals from space, or really weak signals from space, and amplifies them up so that we can hear them. And we tried lots of things. Eventually, the best match that we found was the S2P match from the manufacturers of the components. But we think that if we had optimized with point ports like we did on the Diplexer, we would have gotten a much better result. I have a video on this too. And the other cool thing about this is we are getting 28 dB of gain on the 2 meter. And that is actually higher than the data sheet showed for this little low noise amplifier chip. So it's amazing that we're able to do this all and compress it all into a short 20-minute presentation. So this is what we've done in 3 years. We built the helical antenna, which is circularly polarized to catch that frisbee in any orientation. And we added the second winding because we needed the other UHF signal. We also have our antenna rotors to move that beam up and down to track our satellites. And we also have our tracking software to track the satellites with our Silas controller. Now we also have our bias key on our Diplexer for taking the 2 signals and forcing them down one wire to split them out again. And we also have our LNAs. Now, there's one more thing I didn't mention in the presentation, and that is that the LNAs need to be turned off when we are transmitting, so we don't fry them when we send 100 watts through them. So we have a relay that switches them to bypass mode using this push-to-talk circuit, which I didn't show here. And that just turns off the LNAs when we're not transmitting. Now, my favorite part of the presentation is this, the things to do. We have to mount our helical antenna, we have to run our feed line, and then we have to mount the cameras so we can calibrate on things and make sure it's working. And finally, we have to call the ISS, the entire reason that we did this. We'll be having questions now.
So, as moderator, I get to take the first question. I'm sure someone's going to want to ask when you're ready to test and be an early access customer for Allegro XAI. But before we get there, I'm going to ask a softball question. Have you approached Lego about a sponsorship yet?
No, I haven't done that yet.
Okay, well that might be somewhere you go. So, do we have any questions from the audience? The handsome gentleman in the back.
Zeke, how do you fund this project? Do you have lots of car washes, or what? What's this cost?
Well, my dad's business pays for a lot of it.
No, it doesn't. That's why we're here.
What business is your father in?
He's in security, Linux security support. And so we've just been, I don't even know how much this thing costs. We just don't keep track of that sort of thing and hope we get motivated.
That will change. Anybody else with a particular question? Did
you
we got?
you in the back.
Does the ISS continually monitor the VHF frequency that you're going to?
Only when someone's at the radio. Yeah. So we're going to try calling when they're above, say something like, we only have you for 10 minutes. If you're at the radio, please answer. Or something along those lines. If we really can't get it, then we're probably going to try to organize something and get a person onto the radio so we can talk. You?
Have you tested the LNA circuit yet? Have you actually tried anything with it or not?
So we tested the push-to-talk circuit, and it works. It does turn off when we transmit the radio, so now it just needs to be put up, basically. We have to mount the antenna. And we also have to match the antenna to 50 ohms, because
Right,
that's
which is, yeah.
our impedance.
How do you know you're not amplifying a lot of noise at the same time? Or do you?
We don't know if we're going to just amplify noise with our LNA, or if our LNA is even going to be useful.
Okay.
So we're just trying all these things to try to get them to work.
Okay.
Anyone else? Sherry.
I just have a question. You still have, I mean, you've done tremendous work, and I've watched not all of your videos, but some. Fantastic. How much time do you have to finish the things up? Do you have a specific goal in mind?
We're trying to do it before my birthday.
Oh my goodness. That's like only a matter of weeks.
Yep, we're trying to do it before we leave for Costa Rica.
Hey, okay, good luck. Yeah. I thought maybe another year or two, so that's we're down to the final weeks.
You in the back there?
Yeah, thank you for your presentation. I really enjoyed it. That was good work. But like, if you can do this like again, like, would you like what kind of aspect you would improve on, or you would do differently?
In the presentation?
No.
If we were to redo this project,
Yeah.
Yes.
I don't know what we'd redo differently. I mean, like, we've done the best we could. If we'd have known about it, we would have just used point ports the first time. Yeah. You?
So what's next? What's after this?
So the next big project is to make a phased array antenna, which allows us to point the beam with no moving parts by changing the phase and by turning on and off the antennas at different times to point the beam. And we're also planning on making a giant octocopter with 8 propellers and putting a antenna on each of the propellers so that we can have a phased array antenna 400 feet in the air with our octocopter drone. You in the blue shirt?
Actually, a couple of questions are coming. How did you get access to the software in the first place? And what do you want to say to the ISS?
So we've been working on a list to talk to the ISS. It's not final, and I don't have it here, but we've been working on a list, and I'll post a video about that when we talk. What was your other question again?
The first one was just how you got access to the software in the first place.
We built the software out of C.
No, sorry, no, the Cadence software.
Oh, Cadence software. So we wanted to optimize a match for a power amplifier. And the files for the power amp had Microwave Office or Cadence as an option. So we just chose them because we knew who they were. And that's...
You use on cloud also, right?
Yes, we did test early on cloud, and those models in Clarity were actually made in on cloud. Where is that?
The rocket.
These were made in on cloud. Clarity. Anyone else? Well, if that's it, I think that's the end of the presentation. So thank you.
Yeah, you did a good job. Oh, that's